Hello, I'm Adam, and I will present joint work with Una, Raymond, and Alex. Many real-world problems can be formulated in a multi-agent setting. For instance, a warehouse may deploy a swarm of robots to pick up packages. Multi-agent reinforcement learning also achieves impressive performance in soccer or video games like StarCraft 2. In reinforcement learning, an agent interacts with an environment. At each step, the agent executes an action, upon which the environment will reply with the next state and a reward signal. The agent's goal, roughly speaking, is to maximize the expected reward. Therefore, access to the reward is essential. In this work, we consider multi-agent reinforcement learning in a sparse reward setting. In a sparse reward setting, the agents only receive rewards when a task is completed. The main advantage of sparse reward: it is easy to design and it is broadly applicable. However, it is well known that sparse reward makes policy learning challenging. As a result, in a sparse reward setting, an efficient exploration strategy to quickly find the reward signal is particularly important. Efficient exploration in a multi-agent setting suffers from at least two challenges. First, the agents need to identify states that are worth exploring. In multi-agent reinforcement learning, the size of the state space grows exponentially with the number of agents. As a result, it is infeasible to explore all states, particularly when the number of agents is large. To see this, consider a push-box task. In this task, agents need to collaborate to push a heavy box to a goal in an L by L grid. The agents only see collective reward when the box reaches the goal location. In this task, the state contains the XY location of the agents and the box. In a two-agent case, there are L squared to the power of 3 states to explore, where L squared corresponds to all possible XY locations, and 3 corresponds to the 3 entities in the environment, that is the 2 agents and the 1 box. Similarly, in an n-agent push box task, where n agents need to push the heavy box collaboratively, there are L squared to the power of 1 plus n states to explore. Obviously, it is intractable to visit all states, particularly when n increases. The second challenge for multi-agent exploration: agents must coordinate in order to achieve efficient exploration. For instance, in the two-agent pushbox task introduced on the previous slide, suppose one agent pushes the box to the right and the other agent pushes the box into the opposite direction at the same time. The box goes nowhere. As a result, the agents fail to see any new states due to this incoordination. In contrast, suppose the agents coordinate their behavior, say pushing the box together to the left at the same time. The box will be moved to the left and a new box location is explored. From this example, we see that to explore efficiently, coordination is critical. To address the two challenges, we proposed cooperative multi-agent exploration, CMAE. First, to identify states that are worth exploring, we proposed restricted space exploration. Instead of exploring the full state space, whose size grows exponentially with the number of agents, we first explore an underexplored, low-dimensional restricted space. I will tell you about this restricted space in a bit. Second, to ensure that the agents coordinate their exploration efforts, we propose shared goal exploration. Here, the agents share a common goal while exploring the environment. Because of this shared goal, the agents agree on which states they want to explore and how they want to work together to transition to the desired state. I will present the details of CMAE on the following slides. In CMAE, we decouple the exploration policy and the target policy. Classic deep reinforcement learning methods use the noisy version or an absent greedy version of the target policy to collect data. However, it is well known that the noisy or absent greedy method tends to fail in sparse reward multi-agent environments. For this reason, we decouple the exploration policy and target policy. The exploration policy's goal is to collect data from rarely visited states. In contrast, the target policy's goal is to maximize the environment reward. Here is an overview of CMAE. We first train target policies using some collected data. To collect some data, we use our exploration policy, which determines how to interact with the environment. Specifically, to collect data that contains useful information about the environment, we need to train our exploration policy properly. To ensure the exploration agents coordinate with each other, as discussed previously, the agents should share a common goal. How do we select a shared goal? To this end, we devise a shared goal selection mechanism which selects a rarely visited state from an underexplored low-dimensional restricted space. To find an underexplored restricted space, we propose a tree search-based selection method. I will present details of each of the 5 sections next. First, target policy training. The goal of the target policy is to maximize the external environment reward. The target policy could be trained using any standard off-policy multi-agent reinforcement learning method with data collected by the exploration policy. The exploration policy interacts with the environment, and the collected data is stored in a replay buffer. Ideally, the exploration agents must coordinate to visit underexplored states. To achieve this, the exploration policy is trained to reach a selected shared goal. To train this exploration policy, we reshape the reward in the replay buffer. Specifically, an additional reward is added to the transition tuple, which indicates the goal state that we aim to explore. That is, the agents see an increased positive reward when reaching the shared goal. To make this concrete, consider a 2-agent push-box task. The agents have a shared goal in mind, which requires them to push the box to the bottom left corner. When they manage to push the box to the target, they receive a positive reward. To train the exploration policy, we need shared goals. How do we select shared goals? Roughly speaking, we select a rarely visited state as a shared goal. To count how many times a state is visited, we need to maintain counters. Instead of operating the counters on the full state space, we count in low-dimensional restricted spaces. States which have a low count in a low-dimensional restricted space will be selected as the goal. This mechanism avoids exploring the full state space, whose size grows exponentially. Consider again the 2-agent pushbox task. The full state space contains the XY locations of all agents and the box. A restricted space is the XY location of the box. A counter will count the number of times that each specific box location is visited. The location of the agents will be ignored in this restricted space. Then, a shared goal is a state with a box in a rarely seen location. How do we determine meaningful restricted spaces? Why should we explore low-dimensional restricted spaces in the first place? We observe that while the size of the full state space grows exponentially with the number of agents, the reward function typically depends on a low-dimensional subspace of the state space, which we refer to as a restricted space. Consider the n-agent pushbox test again. The size of the full state space is L squared to the power of 1 plus n. However, the reward function only depends on the box location, whose state space size is L squared. Therefore, instead of exploring the full state space, exploring the restricted space, which contains only the box location, is more efficient. Ideally, we want to select an underexplored restricted space. To do this, as discussed before, we maintain counters for each restricted space under consideration. The counters check the number of times each state within a restricted space was visited. Given these counters, we can compute the state visitation distribution. Intuitively, an underexplored restricted space has a smaller entropy. Using this, restricted spaces with a smaller entropy have a higher probability to be selected. Consider a two-agent push box task. The two heat maps visualize the visitation count of two restricted spaces. The restricted space that contains the agent XY location and the restricted space that contains the box XY location. From the heat map, we see that the restricted space that contains the box XY has much lower entropy than the restricted space that contains the agent XY. Therefore, the restricted space that contains the box XY will have a higher probability to be chosen. However, there is a combinatorial number of possible restricted spaces. Which ones should we start with? We formulate a restricted space search as a tree search problem on a space tree. In a space tree, each node represents a restricted space. Importantly, we start with low-dimensional restricted spaces. Specifically, the space tree is initialized with all one-dimensional restricted spaces. Starting with the initial space tree, utility μk, which is the negative entropy of restricted space Sk, is used to guide the space tree expansion. The restricted space with highest μk will be selected for exploration. In addition, from the selected space, we expand the space tree to include higher dimensional restricted spaces. Specifically, for a selected space Sk, all restricted space of k plus 1 dimensional, which contains Sk as a subset, are added as trial nodes of Sk. Consider a two-agent pushbox task where the state space is 6-dimensional. Therefore, the initial space tree has 6 nodes, which correspond to the x and y location of the two agents and the box. Suppose the restricted space SBX, which represents the x location of the box, has highest utility. SBX will be selected for exploration. That is, we will select a goal from SBX. In addition, to expand the tree, all restricted spaces which are two-dimensional and contain SBX as a subspace are added as trial nodes of SBX. As I just explained, CMAE trains a target policy. For this, we select an underexplored restricted space, from which we select a rarely visited state as a goal. The exploration agents are trained to reach the selected goal collaboratively. Then the trained exploration policy is used to interact with the environment to collect data to train the target policy. Note that we don't select a new restricted space and a shared goal in every episode. We only perform the selection every n episodes. Please see the paper for more details. Let me show you some experimental results next. We evaluate CMAE on multi-agent grid word tasks and the StarCraft 2 multi-agent challenge. In all tasks, the agents only receive reward when the task is solved. For multi-agent grid word, we consider 3 tasks. The first one is a two-agent push box. The second task is pass. In pass, 2 agents start in the left room and are required to transition to the right room. The door only opens when an agent occupies a switch. The last task is secret room. 2 agents operate in 4 rooms. They must end up in the same room on the right. Doors again only open when an agent occupies a switch. Here are some training curves on the three tasks using CMAE and state-of-the-art baselines. The plot shows the average evaluation success rate of the task versus the number of training steps. CMAE solves all tasks within a 3 million environment step budget. In contrast, baselines are struggling to solve the tasks. On two tasks of the StarCraft 2 multi-agent challenge with the sparse reward setting, we obtain results shown on this slide. Again, plotting the average evaluation success rate of the task over a number of training steps. We find CMAE to improve upon baselines. To show limitations of the proposed method, we run experiments on the sparse reward version of the 3S versus 5Z task, which is classified as hard even in the dense reward setting. CMAE as well as all baselines fail to solve the task in the sparse reward setting. In 3S versus 5Z, the only winning strategy is to force the enemies to scatter around the map and attempt to land one by one. Without handcrafted intermediate rewards, we find it is extremely challenging for any approach to learn this strategy. This demonstrates that efficient exploration for multi-agent reinforcement learning in sparse reward setting is still a very challenging and open problem, which requires more attention from the community. To summarize, our CMAE learns efficient, coordinated exploration policies via shared goals and low-dimensional restricted space exploration. Please see us at the poster session for more details. Thank you.